You have to find a way to navigate around the moon during that part of the backside of the moon. And such autonomous systems can provide additional redundancy and help manage the space safety level for manned spacecraft specifically.
Welcome to this new video. Today we'll talk about a thesis around navigation for spacecraft and especially new technologies for navigation. Hi Rachit, can you tell us a bit more about yourself?
Hi Remy, I'm Dr. Rachit Bhatia. I have recently graduated from Utah State University. I originally come from India. I did my bachelor's in mechanical engineering back in India from SRM University. And while doing my bachelor's, I did an internship at Indian Institute of Astrophysics, where I worked on AstroSat satellite, which has now been launched by ISRO. I accepted my PhD offer from Utah State University to work on autonomous space navigation systems. Now I'm working in Boulder, Colorado for SpaceNav as an aerospace engineer.
Actually, when you were working in Bangalore, I was working in Bangalore at the exact same time.
Wow.
And I was driving in front of your office every single day.
So
it's a very, very small world.
It is.
So first, can you tell us a bit more about the different technologies that has been used by spacecraft for navigation?
Yes. Currently, spacecraft navigation is dependent on GPS measurements from GPS constellation, or it depends on the ground tracking by different ground stations. If you're in LEO, if you venture out in deep space, then you are dependent on DSN, Deep Space Network of NASA, or other similar networks by other space agencies. That is the major way of tracking and navigating and communicating with spacecrafts. One of the major technique is also delta DOR, delta differential one-way ranging, which is basically the spacecraft sends the signal to two different widely separated ground stations on the Earth, and then that timing of the signal is used to estimate the position of the state vector of the spacecraft. The TDRS that I mentioned is another NASA constellation that they use. It is a constellation of Earth satellites which relay the signal from the spacecraft to the ground station. In that way, you do not need as many ground stations as you would otherwise need if you are in low Earth orbit. The farther away from Earth you are, the easier it is to track in terms of requiring less ground station and more time to communicate. But then the problem is the transmission power, how you will need more transmission because you're farther away. So yes, those are the major techniques.
What about star tracking?
You can use that, and most of the spacecrafts use that. I should mention here, navigation is divided into two major segments. One is dead reckoning, and then is navigating. When you dead reckon, you can use Star Tracker, that can be used, but IMU system, no, because they drift over time. So you will not be able to, and when I say dead reckon, it basically means that you do not know where you are. You are just lost. You want to get some estimate where you are before starting to reduce that error on your estimate. And you can do that reducing of error by a IMU on board, but for dead reckoning, you will use ground stations or star trackers. So yes, there's another technique, X-ray pulsar, that is being proposed, Then there for deep space is there's a company, Advanced Space, that is working on basically creating these different constellations throughout the solar system to basically create a network and reduce the dependency on a deep space network and then track the spacecraft. So yes.
Extending the GNSS constellations we have today.
Yes.
That's fantastic. You talk about dead reckoning and the fact that GNSS is actually pretty interesting for that, giving references, right? Can you tell us a bit more about the technology you worked on, which seemed to be complementary?
Yes, the idea is that GPS has its own limitations, both security and dynamics wise. There are systems now in place where people can easily hack. It is much more easier than it was thought to be to hack and manipulate the GPS signal. So that is one of the challenge. The other challenge is if you are in a congested environment, say underground, then GPS signal is of low intensity or is not available.
No, it is actually. That's what we do.
I take that statement. Yes, that is a challenge that you are solving. The way you are solving is on the ground. Now you need to solve it in the space as well, because what happens if there's a spacecraft in interplanetary? You cannot use GPS for that. If some spacecraft is in the orbit of Mars, you need a deep space network. You need to communicate with it, or you need star trackers, as you said. You will need some other innovative navigation techniques that are coming up, say pulsars, etc. So that is the whole idea. The concept that I'm proposing is we have made these leaps and growth in developing these accelerometers that are very precise. They have low measurement noise, and comparatively low bias. So we have used these accelerometers in the recent decade or so to map the gravitational field of Earth, which we all know is not uniform. So what if now we just reverse the problem? We have we have this gravitational map, and we have these accelerometers on board, and we use these two sets of information to navigate. Again, this won't be very helpful for dead reckoning in first place. We will still need dead reckoning, but it can be helpful to reduce the dependence on deep space network, and you can use that part of the bandwidth for communicating other scientific measurements and important aspects of the mission.
So it can be some sort of new augmentation for deep space.
Yes. Again, there can be a number of applications back on Earth as well. I'm aware there are companies that are actually already looking into the potential of this. There's AOSense in California. There is in connection with Stanford University, and they are working on developing these types of sensors, quantum sensors, for the government and for these applications. Then there's another company in Singapore which is also looking at the applications on ground for navigation purposes and solving the problem that you're saying can be solved for GPS denied, basically solving GPS denied environment problems. The fun fact is these the gravity gradiometers and the precise advanced accelerometers that are coming up, they have been previously used for navigation, and they have been used in submarines previously.
Interesting.
And it is because until 90s, I think even now they are being used, but until 90s they were proprietary, they were kept secret. And then there was this movie about it where they accidentally ended up showing one of the system on board a submarine, and it was made public then that these systems are being used for navigation. So yeah, it is interesting history behind that.
So you talked about mapping. You said that mapping would be necessary for that. Is pure theoretical mapping enough?
you will need actual measurements, because when you say theoretical mapping, then that would be just based upon the two body. To clarify, this is the map, the gravitational field map that we are talking about.
Yes.
And for a body like Earth, where the variation in Earth's gravity is not as much as we see on the moon, which is much more irregular. So, and that was another part of my my dissertation, where we showed that what order of the map you need to tap the measurement up to sustain, and we found that 4x4 and 8x8 order of a spherical harmonics will be sufficient. But now, if think about if a body is really irregular, say an asteroid, then you basically can just use two-body dynamics. Just observe the dynamics are of the body around other gravitational objects, and you can estimate some gravitational acceleration, different sides and different places on the object, and then you can send a spacecraft to basically use that theoretical gravitational map to navigate. Over time, it can definitely be improved to not just navigate, to also improve the map. So it has different application.
As we see more and more companies working on space missions around the moon, then away from the moon, you're working on that. What do you think would be the best approach on building those maps for the moon, for instance?
We already have a map for moon, because that is how what I'm using. Actually, you can go on one of the NASA website and basically view that map. You can view all the surface. We know so much about moon already, and not just moon. We have these maps for many other objects in our solar system. Now the question is whether that estimate, that map, because it all depends on the resolution. When I was talking about the order of the spherical harmonics, it basically reflects the resolution. What is the resolution on that map? So will that estimate will be sufficient? Will that map will be sufficient? That is a good question. For moon, that based on my results and my simulation right now, I'm seeing that it is sufficient. The more the irregularity, the easier it is to navigate, in terms of you can see those different parts of the object distinctly, and it is basically feed tracking. Instead of tracking individual features optically, you're tracking gravitational part of those features, how the gravity is changing, and those rifts and valleys and cliffs, you can see those in gravitational map, and you can then know which side of the object and which orbit we are in, and that is what serves the purpose.
And that has been done by former space missions, right?
For the moon, yes, they have these very good ground map of moon, and they do track those craters, distinct craters that for navigation. So that is another technique to navigate, which I forgot to highlight in the previous answer. But that is another technique that you can use to navigate around a body. But then again, it depends on the lighting condition, on how easily you can recognize those distinct features. So there's that technique, that trick in there. But with the gravitation, you do not. It is much more omnipresent and much more general in approach, because you do not depend on the type of weather back on Earth, or type of lighting condition in space, etc.
So you're working with all those dead reckoning solutions, Starbase, Craterbase, GNSS, in order to build the references.
Right now, this is the first part of the study, where we are basically getting started. So what we do is we say that there is a spacecraft in low lunar orbit, which has an error in its estimate, in its position, say by a kilometer, by 10 kilometer. We set this parameter initially, and then we go on to use our advanced accelerometers on board to not just navigate around the moon, but also basically know the attitude. That is another part of the problem that I've added in my thesis, which is unique, where we can know what is the orientation of the spacecraft just using the same sensors. Now, the next part of the study could be to look into much more specifics of the problem, to see what other techniques would be useful for dead reckoning, and it can be incorporated into the same system reasonably, say by feature tracking, because or we do need some kind of ground communication, and we cannot expand that part. So that is what will be looked into the future.
Can you tell us like where you want to take this work in the future?
Yes. So I'm for my job, I'm not working on the same problem that I was working for PhD, but it uses the same tools to work on problems which are orbital debris, risk collision avoidance, etc. Now, for the part of my PhD project, I would love to work more on it, and I try to. I'm actually anticipating one journal paper pretty soon, and then
It's exciting.
it is, and then another one once my lunar results are all documented. Not much of these sensors are being used for the application that we are proposing, but they will be. That is at least what my expectation is. The last part of it would be to incorporate the hardware of the sensors, which would be more trickier. But yes, and that is what I can envision my role to be, to at least finish all the theoretical part and go to the industry and say, this can be the solution for future of space navigation. We really need to test this.
And that was conversation with Dr. Rachit Bhatia. Thank you so much for your time today.
Thank you very much.
Don't hesitate to like, share this video, and I'll see you for another interview.